All right, so I took a little break from making videos and I figured it's time to get started again. Um, this video is about the chain rule. The video I did, I think it was called the chain rule through the lens of integration. Tries to get a numerical feel for what's going on. I'm not sure I picked the best functions. The numbers came out nicely, but I think given what we've done in our Algebra 1 and Algebra 2 classes, uh, I think that the following might be a better way for those students to see what's going on. So I thought I'd share some of that work. Um, and so I'm going to try to approximate the rate of change of the sine of x squared at square root of 3. And y prime, for those of us who have been looking at this here in those algebra classes that know what that symbol means, it's the rate of change of this function at that value. And I asked my students to memorize a lot of the trig ratios, and not that this is, but the square root of 3 is approximately 1.73. And so you divide that by 2.87. I think it's important to have a feel for numbers. And if you're writing the square root of 3 over 2 when you're doing your trig, you should have a feel for the size of that number. If not, I don't think you have a feel for the process at all. So memorize those values, get your calculator out, and make sure that if you see root 2 over 2, you get a feel for the decimal. Okay. And so I think we can estimate this. And so I did an estimation and then I checked it, to see how far off that estimation was from the actual rate of change of this function at the square root of 3. All right, so it needs a little bit of prep work for those of you who are looking at this video and haven't taken those classes. Let's take a look at x squared and the layering process, which is really what Newton saw, but he saw it differently. He saw it as he squeezed the rate of change from a smaller square to a bigger one. Let's just look at x, and then we got our dx and our dx and our x side lengths, right? We can see that our change in y, we'll call it dy, is equal to 2x dx, right? X times dx is that area, another x times dx is that area. So you got two of them. And then you can see how that step translates into dy over dx equals 2x, right? And I've got some table values here for the quadratic, which is just a fancy term for the rectangle. And this particular rectangle is the most important one, where the sides are equal. So much of math is based on this. And can you see this video? Yeah, I guess you can. I got the lights on. So 0.001, 3 decimal places. And if we just look at the first 3 decimal places here, it's not changing. And that's why x squared is flat at that instant. And then if you look at these values, pause the video and look at them, you can see that the slopes at the user-friendly numbers are going up at 2-to-1 ratio. And I pushed this one out a little bit further with 4 decimal places, and that's moving you towards understanding limits. So give that some thought. And then I think I drew, oh yeah, I did draw some of those slopes. So at the user-friendly numbers, we're not changing at 0. At 1, we're going up at 2-to-1. At 2, we're going up at 4-to-1. And of course, decreasing on the other side. And you get a little feel for rates of change at some of those instances. So at 1, you're going up at 1-to-1. At 2, you're going up at 4-to-1. At 3, you're going up at 6-to-1. And these table values help validate that. So it's a layering process. That's what a derivative is. It's one of those layers of change. Adding up all those layers is what integration is about. Just planting some seeds here. All right, so back to where we were. So we, in Algebra 1, Algebra 2, actually do a little graphing with sinusoids to get students more time to think about it during their high school careers. And so we've established the square root of 3 is approximately 1.73. And so if I use that number because it brings us to a nice place on the sine function. So here's your sine function over here. At 3, students know where we're at just before we get to pi, and the sine of pi is 0. And if you're looking at this video, I'm assuming you've already had your trig and all the kind of preliminary things you need to know to understand this discussion. So I'm going to blow this up a little bit. I'm going to take this and look at the sine function at that instant. So the radian measurements are getting bigger, but your altitudes are getting smaller. And so I blow that up some more. And so 3 might be here. And so let's look at this altitude, right? Never bigger than 1, the sine function. And at this instant, you have that altitude. At this instant, you have that altitude. And you can see they're coming down. So we're moving in the negative direction for the altitudes, but the radians are going in the positive direction. So I hope you can see that at pi, I can't even, the arc length is about the same as the altitude. And at pi, they are the same, exactly the same. So we have a -1 to 1 rate of change of the sine function, right, at pi. And 3 is not too far from pi. So that change in x, very, very small, 0.14, right, roughly. All right. So if we, from the standpoint of calculus, which is usually just memorizing the rule, which is why I'm doing this video, because if you don't have a feel for the numbers, I'm not sure you have a feel for the calculation. So what we really have is the sine function on the x-squared axis. Well, I did that here. So we're on the x-squared axis. So what happens for x squared? Well, x squared are your angles, right? This is all about angles, what's inside that parentheses. And so what is happening with the angles? Oh, not much change in x, but a huge change in, arc length. And so the sine of x squared basically looks something that accelerates as you go forward. Your x values, which are radian measurements, which are distances on the circumference of the circle, just start to do what? Start to rotate faster and faster and faster and faster and faster. And so that gives us this visualization. Oh. All right, so back to calculus now. So the sine of x squared, the derivative of the sine function, the cosine function, we can show that quickly here. Here you're going up at 1 to 1 at the maximum value at pi over 2. At pi over 2, you have a flat slope, 0. Then we're back to -1. Then we're back to 0. And then we're back to a curve. And that curve is your cosine curve. Okay, so just planting some seeds here. All right, so now the rule. The rule is take the derivative of the sine, which is cosine, with respect to where you are on the graph. And that x squared is telling you that. And we can look at this one last time. The derivative of x squared, I think we can see, is 2 times x. So y prime is 2 times x. That's a notation for the same as the change in y over the change in x. Just different notation. And the change in y, we can use delta y, delta x to get a little feel for the notation that I'm using. For those of you who are considering this for the first time. Back to where I was. And so we're on the x squared axis. And so you can see on the x squared axis, well, that's the x-axis here. On the x squared axis, the sine function on the x squared axis is all about acceleration here as we move to the right. All right, so hope you follow me. So I picked the square root of 3 because the square root of 3 squared is 3. And we've talked about, so cosine of 3. You can go to the cosine curve, and where's 3? 3 is near -1, right? 3.14 gets you. So I estimated the cosine of 3 to be -1, which is on the cosine, we're talking widths. Right? And over here, it is -1, and 3 is pretty close. So that's an estimation. And I doubled the square root of 3, which is 3.46, right? Which gave me an approximation of minus 3.46. And what was y prime when I put it into the calculator? Turned out to be -3.429. So I did this without the calculator. Here's the answer with the calculator. And I did that because I think To understand math, you got to have a feel for numbers. You got to play with numbers. And I just did. All right, so I'll post this, and it's real early morning here, and I haven't done this in a while, so I don't know how well that was understood, but it doesn't matter because some seeds get planted, and you get to hear it again at the next level. All right, have a good day.